Good evening. I'm Rafid Ahmed Mahmood from Team Passphrase. Me and my teammates Shomen Dash, Nazia Tasneem, Ishtiaq Shihab, and Mohammad Fayyaz Khan are going to present our solution for the traffic detection problem and competition organized by Dhaka AI. Our task for this competition was to detect and classify different types of vehicles from traffic images. Object detection is an active research domain with a lot of existing solutions. Many of these proposed solutions try to solve the generic problem of object detection, while others focus on adapting specific domain characteristics. Since we are all newcomers,
Excuse me, so I think I need to interrupt you again, and maybe you can switch off your speaker, so you just only speak. Maybe from your laptop, it's creating this echo. If I have to say you something, I will write you. Okay? Yeah, go on. Thanks.
okay. Uh, Since we are all newcomers to this field and lacked the required knowledge and hardware to run many of these large and complex solutions, we primarily focused on understanding the core concepts of these solutions and tried to adapt them for this task. The competition posed an extra level of difficulty because of the density and diversity of vehicle classes and the extremely low amount of data that was provided. Moreover, a large portion of the provided data was mislabeled that made it harder to train models at the early phases of the competition. To cope with these limitations, we had to deploy different data engineering techniques like data cleaning and verification, which provided us with a much needed boost to our performance. Since we are working with such a low amount of data, it was not feasible to train models from scratch. So we had to test and evaluate different pre-trained object detector models to see which ones were more effective in capturing the characteristics of the data and generalizing to our problem domain. After selecting the models, we focused parallelly on different aspects to boost our performance. We prepared the data so that it can be more compatible with the selected models. Experimented with hyperparameters of the models to find the best way to fit them to the data, and then try different ways of collaboration between models to ensure that we get the best of all the models. This enabled us to come up with a solution that was simple yet robust enough to work even with so many constraints and enabled us to achieve our position on the leaderboard. And now my teammate Nazia Tasneem will take over to explain the process in detail.
Thank you, Rafid. I hope everyone can hear me. Okay, my name is Nazia and I will be talking about our data preparations. Although the necessity of data pre-processing has already been pre-established by the previous presenters, I would still like to elaborate on it and emphasize how it was one of our main focus points, which ultimately improved our accuracies on the leaderboard. The common knowledge in machine learning is that unless you use data in a sufficient quality and sufficient quantity, the model accuracy, no matter what architecture, is bound to suffer. However, the challenge here for us was how much control we, as developers, had over the dataset. Of course, striving to collect more high-quality data would almost always improve the model performance, but as students, we had severe resource and time constraints. Specifically, it is especially tough to collect publicly available datasets similar to the given Dhaka AI one. To get started, we spent a significant time in the early stages looking for datasets with similar traffic dynamics and geolocations as Dhaka. For example, we tried to use vehicle datasets from Nepal and India, but we couldn't actually use them in the end. Fortunately, we managed to find an open data source of Bangladeshi vehicles, which we could only use partially. In this, from the class distribution of that external dataset, it is clear that it does not completely match the Dhaka AI data. So we had to further clean this dataset to use for our purpose. So in the next slide, we can see the usable and unused classes from our external dataset. Additionally, at one stage, we even thought about going out, taking photos of roads, annotating them by hand, and creating our own dataset. But as we said before, we lack the proper logistics and, more importantly, the time. Moving on, upon having a decent sized dataset, we try to explore it from as many angles as we could think of. As the first obvious step, we visually assess the dataset and got a feel of its quality. We removed the corrupted images and metadata. At this stage, we also denoise the VOC annotations by relabeling them with external tools like label.img and removing the wrong annotations. Here you can see a sample visualizations of our cleaned dataset. In the following slide, we go more in depth and look at the height-width distribution of our dataset. It's clear that the image height and width clusters between approximately 900 to 1800 pixels, with some large images with over 4,000 pixels. For most cutting-edge models in current days, it is not possible to fit even a single 4K image per GPU due to memory constraints. In that case, downsampling large images to smaller scale is the safest option, which is why we resized our whole dataset to 1024 by 1024. Next, we explore the class distribution of the dataset. Now, even with our external data, we see how skewed the class distribution is, although we only got to use around 600 images from our external source. Now, here we go into more fine details and start looking at the area distribution of the bounding boxes. This helped us calculate optimum anchor boxes for our training algorithms. The trail of the distribution tells us we have few instances with extreme aspect ratios. After these initial analysis, we proceed to improve the variation of the dataset and start the data augmentation step. Augmentation for object detection task is particularly using heavy spatial transformation can easily introduce false data points and thus do more harm than good, which is why we try to minimize such type of spatial transformation altogether. However, this step is explained in more details elaborately by my team in the next segment. Finally, we also had to convert the dataset to match the various trial model formats like TF records and COCO format 2. And this is where I wrap up and pass the next segment to my teammate Showman. Thank you.
Hello, I am Showman. Good evening. In this section, I will be talking about our model selection and optimizations, which include selecting the best group of models for transfer learning and optimizing their baseline performances. As discussed earlier, we were severely constrained on the amount of data provided for the competition. Even after cleaning and adding external data, this problem remained. So instead of training models from scratch, we opted for transfer learning. Transfer learning is a very useful when using complex and deep models on low resource datasets to prevent overfitting. All our models were loaded with pre-trained MS COCO weights. To evaluate models, we used a K4 stratified cross-validation. Selecting a proper validation set for model evaluation is a very important step in deep learning. Stratified split ensures that the classes are divided equally in all folds and the model is not biased towards any specific split. Primarily, we started experimenting with efficient date, which is currently the state of the art for object detection on the MS COCO benchmark. Unfortunately, we failed to replicate this performance on our dataset. Even with many alterations, all efficient date versions consistently showed poor performance. As we can see, we only achieved a maximum of 19% validation MAP using efficient date D6. After that, we moved on to experimenting with faster RCNN. We used faster RCNN with ResNet backbone and got a 44% validation score. This acted as our primary baseline for further experiments. At this stage, instead of optimizing any single model, we tried other existing models to verify which architecture can best fit the trained data. As we were restricted by our hardware limitations, so we could not try a lot of models. To this end, we tried YOLO V3 and V5, which are both single-shot detection networks. We tried Panoptic FPN with a ResNet 101 backend, and lastly, Cascaded RCNN, which is an improvement on faster RCNN with stacked modules. We see that
5 minutes left.
we see that YOLO 5 and cascaded RCNN provide the best baseline performances with transfer learning. After selecting the models, we tried a lot of different optimization techniques for improving their performance. We gained a considerable boost in performance through both trained data augmentation and test time augmentation. For training, we used various augmentations, among which mix-up, mosaic, cut mix, and color transforms are noteworthy. For hyperparameter tuning, we used a genetic evolution algorithm. This is similar to Bayesian search, where it tries to find the best parameter from the search space based on a fitness function over multiple generations. After that, we tried different ensemble techniques, among which weighted boxes fusion gave the best results. WBF uses the output boxes from all the models and calculates the best overlap using a weighted fusion algorithm. This reasoning behind using WBF is typically ensembling techniques like NMS or soft NMS can only select the boxes that were produced during inference. But WBF uses the predicted bounding boxes as reference and generates a new box that has the maximum overlap and confidence. As we were not required to produce real-time predictions, ensembling with WBF was a better choice. Finally, we spent a considerable time fine-tuning the confidence thresholds. Analyzing the evaluation function, we found that false positives have a large negative impact on the leaderboard score. Since we had very limited submissions, it was not possible to check all thresholds by manually submitting for every model and variation. For this, we manually labeled a section of the test data and replicated the leaderboard evaluation function. This helped us get a considerable boost at the last stages of the competition, as we were able to fine-tune our model thresholds accurately. A collection of different experiments that we conducted is shown here. We see that ensembling a large number of models greatly hampered our performance. One possible explanation for this is because of the way WBF ensembles the outputs. Using multiple weak performing models introduces more false positives in contrast to a lower number of strong models. So instead of using a complex pipeline, we selected the best individual models and did a simple stepwise fusion. The summary of our train and inference pipeline is shown here. We think this simplicity helped us in our performance on the private set. Throughout the competition, we incrementally improved our ranking and performance through meticulous experimentation and fine-tuning. Since from the beginning, we were heavily constrained with resources, we could not try all experiments that we wanted to. Even with this low data, we were able to build a robust pipeline that can generalize significantly to unseen data. Our ranking would have surely improved if we could gather more external data and experiment with more models and optimization techniques, such as improving cross-validation of models, experiment with custom layers, experiment with different loss functions, and some of the newer state-of-the-art semi-supervised learning algorithms. To summarize our experience and contributions of this competition, with very little prior experience, we are astounded with the results we have achieved. We learned a lot of practical deep learning and computer vision concepts, which will surely help each of us in our future careers. Thank you. All questions are welcome.
Thank you very much.